Hello, I'm Shinya Shiroshita from Preferred Networks. Today, I'd like to introduce our research named Behaviorally Diverse Traffic Simulation via Reinforced Learning about the diverse driving policy generation algorithms for autonomous driving. This work is a joint research with Toyota Research Institute and supported by Toyota Research Institute Advanced Development. Traffic simulation is becoming an important tool for planner development. Many simulators such as Kara, Sumo, Fluids, and benchmarks such as common roads have been developed. Many research works utilize them to test their planners. Existing simulators focus on various aspects such as realistic sensor data, dynamics, and traffic participants. However, these simulators provide behavior models from some simple rule-based algorithms, learning-based algorithms, or algorithms added by users. These algorithms are independently developed, so it is unclear how to combine these models as a diverse policy set. Diverse behavior models helps develop a reliable safety validator for planner testing and future trajectory predictor considering the wider possibility. Our research target is to resolve the challenges of developing a diverse policy set. One big challenge for diverse behavior modeling is to balance diversity with high driving skills, meaning safe but not too conservative policies. One way to obtain diversity is to generate highly random trajectories, but this approach will generate a huge number of failed trajectories and is inefficient for testing purposes. Another approach is to use a collection of scripted or learning-based policies. Although they have good driving skills, it is hard to cover a wide range of behaviors since they may converge into similar behaviors. Our approach aims to develop a set of a fixed number of policies holding both diversity and driving skills. It helps efficient testing and behavior prediction with less amount of policies. Existing behavior modeling approaches consist of three types of methods. One kind of method is based on rule-based planners with controllable parameters. One drawback is that it is difficult to find a set of good driving parameters that generate quite different behaviors. There often exists a trade-off between behavior diversity and driving performance. Another approach is to learn from real-world data such as social GAN. Data-driven approaches, however, have difficulty in training rare events such as near-collision cases. Moreover, it may require extrapolation to cover out-of-data behaviors. Recently, several reinforcement learning approaches have been proposed. As far as we know, these approaches obtain diversity by changing environmental parameters such as how likely each policy yields. It is specific to some traffic scenes and would need to design different parameter settings for different traffic scenes. Our goal is to provide a set of k diverse policies from an easily tunable policy generator. To achieve this, we also tackle an open question of how to measure behavioral diversity quantitatively. We propose two measures as a criterion for diverse policy selection and an indicator of possible behavior coverage. Our research contributions consist of the following three parts. One contribution is about diverse and highly skilled policy generation algorithms. We utilize reinforcement learning's exploration skills and efficient policy selection criteria based on the furthest point sampling. Another contribution is about two quantitative diversity evaluation measures. One is named overall diversity for coverage of possible behaviors, and the other is inter-policy diversity for judging how different two policies are. The third contribution is that we examined how diverse are the policies we generate with our method in an intersection traffic scene. Note that we also applied our diverse policy selection method to planner testing, to find diverse failure cases. We will publish this result in ITSC 2020. Now, I'd like to introduce our first contribution, diverse policy generation algorithms. Our method's basic strategy is to create a lot of candidate policies and then pick up a diverse subset. In candidate generation, we employ reinforcement learning to generate diverse policies. We utilize the randomness of initial parameters, exploration skills of RL, and repulsive force during training several RL agents in parallel. For each training policy, the repulsive force is defined by a bonus reward calculated from K divergence of action distribution to the other policies. This idea is a modification of diversity-driven exploration, which originally keeps the current policy away from the recent training snapshot to enhance exploration skills. The selection step consists of 3 sub-steps. First, we filter candidates based on success ratio so that the remaining policies have certain driving skills. We define success ratio as a proportion of successful scenarios. Afterwards, we randomly pick up a policy as an initial set. Then, we repeatedly append a new policy based on farthest point sampling. We choose the second policy as the most distinct one from the first policy. The third one is selected by the farthest policy from the minimum distance of the policy 1 and 2. We continue this repetition until we get k policies and return the set as an output. The distance of 2 policies is defined by the trajectory distances over test scenarios. We denote the distance as inter-policy diversity of 2 policies. Details are shown in the next slide. Another contribution of our research is evaluation metrics. We propose 2 kinds of metrics aimed at different purposes. Both measures evaluate diversity from generated trajectory in several scenarios. One metric is inter-policy diversity. It measures how different trajectory each policy generates. The trajectory distance is based on the average Euclidean distance of the center of 2 vehicles marginalized over time. We calculate distances of 2 policies over scenarios where both policies have successful trajectories. The final output is an average of the all policy pairs distances. The larger value represents spatially distinct behaviors. The other measure is overall diversity to measure coverage of possible behaviors. The basic idea is to calculate the closeness to a certain trajectory set, approximating all possible behaviors. We denote the set as reference trajectories. We generated reference trajectories using Brownian bridges, a probabilistic process whose initial and final states are fixed. We perturb the transitions on a predefined route. Since the pure random walk ignores vehicle dynamics, we approximate them by a trajectory of a proportion control agent tracing it. We finally get reference trajectory by removing unsuccessful trajectories. Overall diversity is defined as follows. Firstly, we consider a trajectory pairing from the sampled trajectories to the reference trajectories. Afterwards, we consider an average distance of pairwise trajectory distances. Wasserstein distance is the minimum average distance from all pairing, allowing some pair with less than weight 1. We marginalize this value by scenarios to get the final output. Note that the lower overall diversity means better coverage of the scene. Let us move to the third contribution, an experimental analysis. I'd like to share our intersection simulation environment first. We consider an intersection environment with multi-agent settings. Each agent tries to run its specified route without collision in a decentralized manner. Each agent can observe the surrounding environment from LiDAR-like information, so occlusion must be considered. For the surrounding vehicles policies, we use two types of models for different evaluation purposes. In a quantitative evaluation settings, we employ a fixed RL policy unaware of the ego vehicle to measure the diversity with the same surrounding behaviors. In qualitative settings, the ego policy runs interactive behaviors of all vehicles, repeatedly switching one by one, using copies of the own policy to the other vehicles. In summary, the environment is a multi-agent setting requiring the understanding of complex transition and interactions. You can see more details in our paper. We will show experimental results in the next few slides. This page shows results in the algorithm scenes. Each column describes different policy generation algorithms with different level of diversity. All of them follow our policy generation strategy. The first row shows the XY positional transition of the right turn vehicle from left to down, avoiding a fixed trajectory of the upcoming vehicle. The second row shows speed profiles during the episode. The right-hand ones have better diversity scores, that is, higher inter-policy diversity and lower overall diversity. As shown in the figure, ones with better diversity scores shows more variation of position speed profiles. This video shows superimposed 50 policies in 9 right straight intersection scenes. These scenarios have different initial position and speeds. The left side has a lower diversity score and the right side has a higher one. As shown in the video, higher diversity covers a wider range of interactions. We also examine the cooperation abilities in 3 kinds of traffic scenes. The figure shows the difference in behaviors in the same right straight traffic scenario. Each color represents the positions of 2 vehicles at the same time. You can see various types of interactions in the policy set. For example, many policies make the right turn vehicle yield to the other, but they took different strategies. Most of them use the deceleration to keep a tight turn, whereas policy 3 and 6 shows a relaxed turn by detouring. On the other hand, the right turn vehicle didn't yield in policy 4 and 7. This movie shows the result of interactions in the various traffic scenes. We have experiment on a right straight intersection, a straight intersection, and 4 directional intersection respectively. Each color shows a set of vehicles running under the same policy. In all of the scenes, the policy set generates a variety of interactions. We propose diverse policy generation algorithms as well as 2 quantitative evaluation metrics. We confirm the effectiveness of our methods in the intersection traffic simulation. Potential future extensions are as follows. The first one is that we can integrate other generation methods to obtain more diversity. The second is that we could utilize real-world data to mimic human-like behaviors to measure the plausibility of each trajectory. It is highly beneficial to application purposes. Finally, we may consider the usage of the behavior prediction modules mounted on the test vehicle. Thank you for listening.